Okay, we've talked about angles. Now we are going to define the trig functions. And you may be familiar with trig function definition that involves triangles. That's the basic trig function definition and the initial one that is used. The only trouble with the basic triangle definition is that it only allows you to look at angles up to 90 degrees. And so to look at angles bigger than 90 degrees, we just need to generalize that slightly, and we need to be able to look at those angles in the plane as we were doing when we looked at angles. We want to talk about all kinds of angle measurements. So in general, if we draw an angle, how do we determine the sine, the cosine, the tangent, the cosecant, the secant, and the cotangent? Those are the 6 trig functions of that angle. And here's how we do it. So the setup is like this. For the setup, I want to focus on this picture. Now, here we always draw our angles so that the positive x-axis is where the angle begins, and then that's the initial side of the angle, and then the terminal side of the angle. Here it's been drawn up here in the second quadrant, but of course it could go anywhere you want. And the idea is that positive x-axis, that's the initial side, and then on the terminal side we have a single point P with coordinates a comma b. A is the x-coordinate and b is the y-coordinate for this point P. And if that's the setup, and if we're interested in the angle x, which goes in between that positive x-axis and our terminal side here, we define the trig functions of x as follows. They're essentially like a ratios of these 3 values, the a and the b, and then this guy r. So what is r? R is the distance from the center out to P. And by thinking of this right triangle right here, there's a right angle right there in between horizontal and vertical. This distance is length A, and this distance is length B. That's from the x and the y coordinates. R is just the length of the third side. It's the length C. And so, first of all, we can calculate r by noting that a squared plus b squared is equal to r squared, and therefore, if we solve for r by taking the square root, r is equal to the square root of a squared plus b squared. Now, what's going to be useful to us here is that we allow this point AB to be essentially any point, and in particular, the x and the y can be positive or negative. And that means that we might have that point in the second quadrant, in the third, in the fourth, or in the first quadrant. It could be anywhere. And that means that these guys that we're looking at, the sides, we're gonna associate with them either positive or negative numbers. So it's not strictly like the length of the side. The idea is the length of the side, but it could be a negative or it could be a positive. In this case, since the point is in the second quadrant, the x-coordinate is negative, the a is negative, and the y-coordinate is positive, b is positive. Okay, something to notice, r, this dist guy, is always a positive number because it's the positive square root of a squared plus b squared. Okay, so from these 3 numbers, the number r, the number a, and the number b, and I think of them in a triangle here, I think of r as like the hypotenuse, a is like the bottom, and b is like the left-hand side. Although, of course, a and b could be negatives. That's the thing to keep in your head. We define the trig functions as follows. For this angle x, the sine of x is equal to b divided by r. And if we think of this as our basic triangle, it's this, the vertical side, divided by the hypotenuse. Cosine is equal to a divided by r, so the cosine is somehow the bottom divided by the hypotenuse. And the tangent is a over b. So a is this distance here, b is here. It's like the bottom divided by that vertical side there. So that's sine, cosine, and tangent. And then cosecant, secant, and cotangent are just what you get when you flip these fractions over. So if we flip over the fraction sine of x, b over r over b, we call that one cosecant. If we flip over cosine as a over r, if we flip that over and make it r over a, we get secant. And for tangent, b over a, if we flip that over, we get cotangent, which is a over b. A few observations about this. So there's 6 trig functions. We tend to think of sine, cosine, and tangent as the basic ones. They're the most familiar ones. But the observation that we just made allows us to make connections between sine and cosine. In particular, between the sine, cosine, tangent, and cosecant, secant, and cotangent. So for example, these are facts. We call these trig identities. These are just equations that just work no matter what angle you're dealing with. So first one is that the cosecant of x, well, it's equal to what you get if you take the sine of x and you flip it upside down. It's 1 over sine of x. And, of course, you can see this in the formula. The cosecant is r over b. And if we're to flip over sine is b over r. If we flip that over, 1 over sine, we're going to flip over this fraction. We're going to get r over b. All right, so cosecant is 1 over sine. Similarly, secant x, which is r over a, that's 1 over cosine. And finally, cotangent of x is 1 over tangent of x. So this is nice because it says if you know sine, cosine, and tangent, then by essentially flipping them over, 1 divided by each of them gives you the other 3, cosecant, secant, and cotangent. Another thing to notice is that there's a relationship between tangent, sine, and cosine. If you take sine of x, that's b over r, and you divide it by cosine of x, that's a over r, and simplify that fraction. It's a little bit of a messy fraction, but you flip the bottom one up to the top and r's cancel, and what you find is that sine of x divided by cosine of x ends up equaling b over a. It's just exactly equal to tangent x. So this gives us another handy fact, another handy trig identity, which is that the tangent of x is equal to sine of x over cosine of x. And there's a similar one for the cotangent of x. Cotangent is 1 over tangent, but cotangent of x is also equal to cosine of x over sine of x. It's just the formula that we had for tangent here, flipped upside down, gives you cotangent. So this is handy in the following sense. These two allow you to take expressions involving cosecant and secant and replace them with expressions involving sine and cosine. This one allows you to take a tangent and replace it with something involving sine and cosine. And this one allows you to take a cotangent and replace it with sine and cosine. That means that we can always translate all of the trig functions into some combinations of sines and cosines, and that's a trick that we'll be using later quite a bit. Okay, so that's the basic definition of the trig functions. And what we want to do now is the following. This is essentially what I'm going to tell you next is the big idea of trig functions. What is a trig function? Well, the angle tells you which direction that terminal side goes. And so for that angle, when we think about moving off in this direction, if we move a certain distance r, we can think how much of that distance r, how much of that movement was made up of vertical movement, and how much of that movement was made up of horizontal movement. And since we're interested for a particular angle in thinking about moving along that angle, any distance we want, and then breaking up the result into a vertical part and a horizontal part, what we do is we just standardize this by saying, what if we only move a distance of 1? So what if we decide to only move a distance of 1 here? What if we make it so that this length r is equal to 1? And if we do that and then consider angles going in all sorts of various directions, but the r part of them is only 1, we get what we call the unit circle. And this is the sort of second big picture that trig functions depend on. This is what we call the unit circle. This is a circle of radius 1, so it's a distance 1 out here. And you can see it's just the same as the picture above, except that we've now set r equal to 1. And what's nice about setting r equal to 1 is that it simplifies all of the definitions. So if this here is a point on the terminal side of our angle, if this is our point P, A comma B, and if r is equal to 1, well, what this allows us to do is, by using those definitions, for example, sine of x is equal to b over 1, which is just b. So the sine of x is just equal in this point to the y-coordinate. When you look at this point on the unit circle, this point has some coordinates, an x and a y, and the y-coordinate is exactly equal to sine. Similarly, the x-coordinate, this guy, this distance here, is the x-coordinate. That x-coordinate is exactly equal to cosine, because we have cosine of x is equal to a over r, which is a over 1, which is just a. And so the beautiful thing about the unit circle is, if I pick a point on the unit circle and I look at the x and y coordinates, the x-coordinate will be the cosine of that angle, and the y-coordinate will be the sine of that angle. Here, the x-coordinate of this point is exactly the cosine of this angle, and the y-coordinate of this point is the sine of this angle. And it's very often, it's useful to think of this picture of a unit circle. Think about coming up with an angle by moving around the unit circle until you reach the angle that you want. And then think of the x-coordinate that you've arrived at and the y-coordinate you've arrived at as the cosine and the sine of your angle. All right, that's going to help us out a lot when we try to visualize what happens as we move around a circle, as we increase the angle, what happens to sine, cosine, and tangent.